me up. Can you do it? Hand over hand. Can you do it? Yeah. A little bit. There you go. That's great. Yeah. Okay. I'm going to relieve you. So can I hold myself up? If I hold on, will this work? Yeah. Yes. Everyone says. And actually, you're right. I can't hold myself up. Yes. I think I go now. Thanks. And if she let go, I really would have fallen. Like she's really holding me up, and I'm really holding myself up. And I'm a really strong guy. But this is even for me. This is too easy, right? You know, like I'm right-handed. Come on, right? So why should it be? Why should it be? I can do that. All right. Well, thank you very much. So let me ask you this then. Suppose I didn't have all these pulleys here. Suppose I just had a single pulley and a rope, and I asked you to hoist me up. What would have happened? If you're strong enough, you probably would have left the ground, right? Because I weigh more than you, so you wouldn't have made it off the ground, right? But in this case, you were, you know, I mean, you were able. It was a little effort on your part, but not that much effort, and you were able to raise me in the air, right? So let's think through what's going on here in a couple different ways. First, let's just figure out, like, let's just draw a free body diagram. First thing I do, the problem, like, this is pretty complicated, right? There's a lot of ropes going on. So how do I make a free body diagram? And first I have to decide a free body diagram of what? All right. So the first thing I do is make a picture of what the situation is. So here's the ceiling, right? Well, okay, it's a bar, but we'll call it ceiling. And there's 3 pulleys on top. I'll draw them schematically. That's these 3 pulleys right here. See, there's 3 pulleys right here. And then there's 3 pulleys down here as well. Okay? So there's 3 pulleys on the bottom part. I think I'll draw these bigger so you can see it. Big pulley. Big pulley, right? Big pulley. All right. So here's 3 pulleys on the ceiling. Now there's 3 pulleys on the chair. Okay? And let's do this. So we have to make some decision what we're going to actually focus on as the system when we go to our free body diagram and our Newton's second law and all that jazz. So let's do it this way. Let's say that here's a chair, here's me sitting here happily, right, arms akimbo, above the ground. These are ideal pulleys. Let's see, did I do this right? I think I did. I should have staggered these a little bit. That's okay. So we'll do this, and we'll have this rope comes up and it's tied on. I think it's tied onto the ceiling right there. It goes around like that, goes around like that, goes around like that. So I just place this in a funny way. So I'm really leaning over to the side here, but if you'll forgive the fact that these are leaning, I meant to draw them more vertically, right? So that's, and obviously it's not the scale. I'm tying the pulleys are big. You get the idea. And then here's the student leaning back, you know, pulling hard, right, up on a stool. All right, holding me up. And there's some tension T in the rope, right? So I think I'm good so far. I think that's correct. Let me just check to make sure I know what's going on the top. Yeah, so here's that guy coming off this pulley. Yes, and here's this inner rope here came off the last pulley and it's tied to the top. So that's what this right here is representing the fact that the rope, the last rope, you know, the end of the rope coming off of, where is it? From right here, the end of the pulley is tied on the top again. That's important. It turns out it really matters exactly what these things are doing. So it's good that we get that right. Okay, so let's call this thing, including the 3 pulleys, let's call that our system. So I include me, and I'm the massive thing here. This chair doesn't weigh anything, right? And the ropes, we're going to assume the ropes and the pulleys are ideal. So really, I'm the only thing that's got any mass anyway, but we're going to include all this stuff in our system. So here's our system, right? That's the first thing you have to figure out. And what's going on? Well, I'm being hoisted by some height, right? She pulled on a rope, and I went up by some height. Let's say that she did it. We'll say that I went up from some height h. So I almost say we just measured it from the bottom of my foot. Doesn't really matter, but some height h. So I was hoisted up some height h. And one question we'd like to ask is, how much work did she perform in order to do this? So there's a couple of questions we can ask. We can say, how much work, student, on me? Another question is, what was the change in the potential energy due to gravity of me? You know, my potential energy due to gravity. What was that? When she did that, right? Well, we see that it's really easy to figure out what my change in potential energy is, right? If my mass is m, what is it? Did my potential energy go up or down when she hoisted me up? Up. Exactly what is it equal to? Do you remember? If my mass is m and I went up height h, what was the change in my potential energy? mgh. You're already done with the part A, right? Or well, I guess, yeah, that's part B. Let's do that. So now let's think about the work she did. So she was pulling the rope some distance and exerting a force. Well, I wasn't accelerating. And you might say, well, yeah, you must have been. You started off still and then you started to move. Okay, there's a little acceleration at the beginning and the end. But if we talk about just a moment in time, just a period right after I start to move, I'm moving at my whatever velocity it is, and she's steadily, let's say she just rocks out, steadily pulling that rope, so that I'm moving at a constant velocity upward, okay, during the whole time. So I'm not being accelerated at any point. Well, that means that there's some constant tension in the rope. Actually, what is the tension in the rope? Question, what's the tension in the rope? That's an important question. You probably have to solve, in order to do this, we have to solve it anyway, to figure out what the work, well, be careful how I say that. We actually don't need to do it to solve this. We can just use conservation of energy once we're comfortable with that. But let's explicitly calculate all these things and see that it works out. Because it doesn't seem like it should in some ways. Right? Okay, so what's the tension going to be? Well, to do that, to get the tension, I would probably solve that, start off with the free body diagram of my system. Say, all right, here's my system right here, right? Free body diagram of me, you know, and the chair, and the pulleys, right? Okay, this is really messy. What matters is it's me, right? That's what's going on. And that sounds very selfish. Right, free body diagram. So what does that look like? Well, I'm going to take a dot for this whole complicated system. And now how many forces are acting on me in this diagram? So it depends on how you break it down, but I would draw 7 separate forces on my free body diagram. What's the first one? Gravity. There's gravity. Now there's a bunch of ropes up here. Well, that's not a bunch of ropes, it's one rope. But in terms of the forces they're exerting, so every one of these ropes, well, it's all one rope, but this piece of the rope has some tension T in it. Whatever that is. And you say, well, wait a minute, is this T the same as that T? Well, as we've talked about a couple times now, if this is an ideal pulley, then you can bank on this T, and this is an ideal rope, you can bank on the fact that this T is the same as that T, which is a godsend, right? It really makes our life easy. So we can say T, 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 okay, all the same tension. But now we've got to be really clear thinking about what these things are doing to me, what forces they're exerting on me. So when this whole thing's holding still, and so she's not hoisting, let's say I'm just holding still for a moment. If I just put a nail, which I wouldn't do, because it's government property, but if I put a nail through that rope in the bottom of the pulley here, right? Now I've got, in a sense, 2 ropes. Or put 2 nails. Put a nail in right here, put a nail in here, cut the rope. It wouldn't change what's going on in the problem. The tension wouldn't change in the rope up here. The same amount of weight is being supported by this configuration of these ropes. This tension is still exerting a force over here on this part of the pulley. Which way is it? This guy right here, what direction is the force he's exerting on this pulley? Down, right? With passion. Up, going up. The force from this rope is up. And every one of these forces are exerting their own force on this. Each one of these ropes are exerting forces on the pulleys here. So that means that I need 1, 2, 3, 4, 5, 6, forces upward, and I'm going to label each one with T, because whatever T, we don't know what T is yet, whatever it is, it's the same for every part of the rope, because all 6 of these pulleys are ideal pulleys, and the rope itself is ideal. Okay, so we've got 6 upward forces due to tension, so we've got 1 downward force mg. What's my acceleration? Even after she starts hoisting me, but what's my acceleration if I'm moving at a constant velocity? 0. So if we use Newton's second law, and then we say, all right, on me, right? Say, oh, F net equals ma. Well, F net, what is it? Well, we have to make a decision about our axis now. Let's call upward the positive y-axis, all right? So let's do this in the y direction. And say, oh, well, I've got 6 upward t, so I got 6 forces of tension in the positive upward direction. See that? But I've got a downward force of mg, and that equals 0 because I'm not accelerating, right? So the tension is just going to be 1/6 of mg by this equation, right? So here, move to the next board. Super. Tension equals 1/6 of mg. And that makes sense. That's how it is that she can pull. I mean, she had to make some effort, partially because these aren't ideal pulleys. So she was overcoming friction in the pulleys as well as my mass, my weight, I should say. If it weren't for that, it would have been a lot easier for you. So these aren't ideal pulleys. But if they were, the tension of the rope would only be 1/6 of my weight. So how much work did she do then? How much work did she do? Well, we know how to calculate the work, right? Work on rope is just going to be the tension. That's how much, because the tension is how much force the rope exerts on her, but she's exerting the same, by Newton's third law, she's exerting the same magnitude of force on the rope. And is the work she's doing positive or negative? So she's pulling, the force is that way, and the rope is also moving that way. So is she doing positive work or negative work on the rope? Positive work, which makes sense. I went up higher in the air as a result of this positive work she did. There's no free lunch. It's all going to work out, right? But how's it going to work out? This is a 1/6 of my mass, right? I should say 1/6 of my weight. Well, how much distance, how much delta, so delta, I'll call it delta x. So I'm defining x to be along the direction of the rope. Whatever, let's say it this way. Delta L, the change in how much length of rope went by. How much rope went by? If I went up by a height of h, how much rope did she have to pull in for me to go up a height of h? So if I move a meter, let's say I move a meter. So this is about a meter, right? If I go, and here's a mark on it, here's a blue mark right here. If I start right here, now how high does that thing go if I go 1 meter? Oop, it's all bunched up. Oh. Did it go up a meter? How about I'll go back down again? Oh, no, I won't. Did it go a whole meter? No, I went about that far. What is that? It's about a 1/6 of a meter. Why? Because the entire length of rope I've moved over here, I have to parcel it out to these 6 pieces of rope over here. So delta L up there is the change in the height times 6. Because if I actually, so in that case, I only went up a 6 of a meter. If I went up a whole, or whatever, if I went up a distance h, that means the amount of rope she had to pull was 6 times h. And I just demonstrated it, but the way to figure it out is you say, oh, where'd that rope come from? It had to come equally from those 6 pieces of rope. So that means that you get mg over 6, right, times 6h. And that 6's cancel. There's no free lunch, and the amount of work she did was, you guessed it, mgh. So she did the same amount of work as the change I experienced in my gravitational potential energy. In other words, these ropes did the same amount of work on me as the negative work of gravity, right? They cancel out. So in other words, my kinetic energy at the end was the same as it was in the beginning. So my kinetic energy didn't change. But the work energy theorem, that means the net work on me must have been 0. Give me 1 second. And the amount of work she did, she was supplying work to the rope, and then the rope supplied that work to me. The net work on the rope was also 0. The rope did positive work on me, but it did negative work on you, right? Because you did positive work on it. Is that reciprocal? So at the end of the day, right, the rope didn't change its kinetic energy, neither did I, because the work energy theorem applied to each of us individually, and the numbers work out. Yeah. Yeah, that's a great question. There's actually 7 places where I labeled T in that diagram, but note that one over there is touching her, not me. This free body diagram is for me, right? When I make a free body diagram, I have to be really clear about what the system is. So I surrounded the green stuff there, so that's the system, just me and a chair and the pulleys, but not the student. If I included her in that system, then you're right, there'd be other forces. In fact, that'd be complicated because she's standing on the ground and there's other forces. So we have to have all these other forces in the problem. But as it is, I thought the way to solve this is just isolate me and the chair. So that's how I did it, and that's what I was referring. That's why I didn't label it me and then second. But if that weren't true, then you have to worry about other things. Not only would there be a 7, but the angle isn't even right. Even my drawing's not great because those should be vertical. But that right there would not be. It would be at some angle. She was pulling to the side when she did that. So then that would be another complication. But that's okay. But now let's do what you're sort of asking. Like when I grabbed this myself, when I was sitting in the chair and I grabbed onto this myself, and let's say I had it vertical, right? And then hoisted myself up. And I say, how much work did I do to raise myself up by the same amount, by h, right? What's the answer then? Well, so what's work? How do I say it? Me on me. Yeah, I don't know, kind of weird. Let's say how much. Let's do this. I'll say me. Oh, I know how to do it. Me on the rope. So that's one thing we're going to calculate, and we're going to check and see whether that's the same thing as the gravitational potential energy increase that I experienced. Right. Well, what is that? Well, that winds up being. Oh, we did a new free body diagram. So now the free body diagram has mg down, but now it's got how many upward vectors? 1, 2, 3, 4, 5, 6, 7. Right? So 7 times t here. Right? Why is that? Because I'm holding the rope in my hand. Now there are 7 ropes touching me or the pulleys I'm attached to. We have to add all those up. So now we go and do Newton's second law for me in the y direction. And what do we get? We get 7 times t minus mg equals ma in the y direction. Oh, yeah, that's 0. So then the answer is yes. The tension is less. So in fact, I experience less tension. The rope has less tension when I'm holding it compared to when you were holding it off on the side. So tension is mg over 7. But then you might say, well, wait a minute, but that means that when I do this, then I'm getting something for nothing, right? Because there's less tension. So if I pull 6h, don't I get raised up by h? Well, is that true? So how much rope do I have to pull down? How much rope has to pass through my hands in order for me to be raised up by h if I'm holding the rope? 7. And the reason is that I'm in a different position when it's all over. I moved up by h. So there's an extra piece of like this rope. Like the same amount of rope has to come out when I'm pulling it as when you pull it. It's just that because I'm the one holding it, my hands are higher up by h. So you get 7 times. So if I say what's the work me on the rope, right? It's force times distance. Delta y. What is that? Well, it's mg over 7 times 7h, and that's the same old thing, mgh, as it has to be, because that's how high. That's the change in my gravitational potential energy. Where did that potential energy come from? Well, it came from all that work I did, right? I did work on the rope did work on me, gravity did negative work on me. My kinetic energy is the same as it was at the end as it was in the beginning, because no net work was performed on me. But I converted my work into an increase in my potential energy. And the numbers work out. They have to. So no matter how I could have a gazillion, springs and all kinds of funny things happening over here, it'll turn out that conservation of energy is going to be the easy way to get answers for a lot of stuff. We'll do this in depth on Thursday, but if you want to know how fast something's going, right? I love this demo, as you know. It's a roller coaster. That was your age, I used to like roller coasters. Anyway, now I'm just happy to be able to make it home the other day. But if I want to know how fast the ball is moving at some point in this roller coaster, I was ready that time. I want to know how it's going, like right here. Well, one way to figure that out, right, is to use Newton's second law, F equals ma, and you can calculate along here, but it starts getting complicated, right? Because right here, there's a normal force changing direction, and it's slowing down, and it'd be a huge pain. It'd be enormous. It'd be a really awful calculation to try to figure out how fast the ball is going at every stage of the way. In order to finally find out the ultimate thing you want to know is how fast is the ball moving. It was right here. It's awful. A calculation that I wouldn't expect you to be able to do. In fact, it would take some effort for me to figure out how to do it myself. But you don't have to do it. If I ask you how fast is the ball moving right here, well, you can use the work energy theorem, right, to figure out what its kinetic energy will be here compared to what it was when it started. If it starts from rest, what's its initial kinetic energy? 0. And what's the difference? How are you going to calculate, like, what are the forces in the problem? What are the energies in the problem? So it's going to turn out. So this work energy theorem here says, oh, the network. If you can calculate the network, you're okay. But one problem you might have is, well, wait a second. What are the forces acting on the ball as it goes around here? So there's gravity's acting on it. What else is acting on it? Normal force. Take a look at this expression right here. It's very important. So power. One way we can rewrite it, right, is in terms of a dot product between a force and a velocity. Now, if the ball at every stage of the way is moving along the track, so its velocity is tangent to the track, right? Like right here, the ball's moving that way, so the velocity is that way. The normal force is always pointing right to the center. It's a circular path, so it's always pointing to the center right here, right? In fact, if you go around every part of the track, and even if it weren't circular, even the parts that aren't, they're sort of halfway or doing different things, normal force is always pointing perpendicular to the direction of motion, i.e. perpendicular to the velocity. So what is this dot product always for the normal force divided by the velocity? So what's the power? How much power do you get from the normal force? 0. That's really powerful, but it's only a bad joke. It's a really useful observation, because it means that if I want to try to figure out what the change in the kinetic energy is, what the velocity is finally here, from this point to that point, then all I need to worry about is the force of gravity. The normal force doesn't do any work. It can change the direction of the ball, right? It can change the path the ball takes, but it can't speed it up or slow it down, right? And you might be bothered by that. Say, well, wait a minute, because I know that if I just drop the ball into gravity, after 1 second, it's going 10 meters. Excuse me, is that true? It's going 10 meters per second. Yeah, it's going 10 meters a second after 1 second. Whereas if I drop it, if I let it go on here, but when it goes on here, it's not going 10 meters per second. It's going slower than that, right? Because the track prevents it from falling low enough to acquire that much kinetic energy from a bigger loss of potential energy due to gravity. But in fact, it's still the case that the normal force does no work. So if you want to figure out how much change there is in the kinetic energy, or for that matter, the velocity of the ball, you only have to think about gravity. And gravity is easy. Potential energy due to gravity is energy times the change in the height. That's all you have to worry about. That's why this is useful. And you're going to use it on the midterms, and you're going to save yourself, instead of a 5-hour problem, it'll be like a 5-minute problem. Anyway, all right, we'll see you next time.